Cool. So I guess we have started. Okay. Which one? Okay. So what we'll look into today's session is something known as dynamic programming. Okay. Now again, as usual, how many of you have heard about this? In case if you know something, please go ahead and explain. Yeah. Anything is fine. Whatever you want to, whatever you know, whatever you want to explain.
Like trying all possible ways, like, and also storing the previous I mean way,
Results.
yes, previous one instead of retrying again and again, that one.
Okay. Nice.
Okay.
Others?
Simply recursion plus catching.
Recursion plus caching. Good. Others? Any more? Anything else?
No, I don't know anything about DP.
Deva, what do you say?
Nothing more, bro. Okay, I've did everything.
Okay. So yeah. So a good term that you guys have suggested is something as recursion plus caching, right?
Mm.
Okay. So this is one of the topics, probably the most important topics among, I mean, it's almost as equal as graphs. Okay. So dynamic programming, I would say it's more important than graphs, but yeah, I mean, there's a trade-off. Okay. So what's actually dynamic programming is, so what we have learned in recursion, the thing which we have learned in recursion is, given a problem, okay, what happened on that problem is, we would ask its subchildren, or we would ask its subproblem, solve the subproblems and combine and return to the parent or to the top node, right? A problem was decomposed into smaller subproblems and it was solved. Do you guys agree? This
Yeah.
is what we have done on recursion. Okay.
Yeah.
So in general, what happens in recursion is, there is a node, okay, which goes internally to some subchildrens. It itself asks its more subchildren, and at one case we actually stop and again we return back, right? So if you see, I am drawing some arrows. True. So can I say this is a graph? So obviously we have not started, but can I say this looks like a graph at least, right?
Yes,
Yeah.
bro.
So DP is nothing but
Yes.
solving a problem, solving a problem in a DAG. How many of you know this term?
Directed acyclic.
Directed acyclic graph.
Exactly. So DP is solving a problem in a directed acyclic graph. If you have a cycle, that is, let's say if you have something like this, okay? If you have a cycle, then it's not possible to do dynamic programming on this. Why? Because you are saying that I am dependent upon my children. This node will say that I am dependent upon my children. Now this node will say that I am dependent upon you. But again, this is a loop, right? So that's the reason DP cannot be solved on this. Okay. But in general terms, we will not go onto this theory. DP is nothing but we will apply recursion. So what happens on recursion is, there are multiple subchildrens which gets called multiple times. Okay. So in order to not call the same problem again and again, we use something as caching. And what's caching in general? Caching is something that whenever you know the answer, please store it. And whenever again the request comes for the same problem, rather than computing again, return it from there itself. Okay. This is what cache is, right?
Yes, bro.
Correct. So what's generally a cache? Cache is a memory where you store some information, and whenever a request comes to you, if in your cache, if a request is stored, you just return it, right? If it is not stored, what you do, you actually compute the answer, store it in cache, and then return that. Got it?
Yes.
Is it
Yes,
clear?
bro.
Yeah. So the only
Yes.
difference between cache and dynamic programming is, there is one thing, this is known as TTL. How many of you know this term? TTL,
Time to live.
Time to live.
right? TTL, time to live. That is, so in general, when you store in a cache, what happens is in a real application, you actually have to determine when you have to evict your information from cache, right? So sometimes we set something known as TTL, which is for how much amount of time we want our answer to be remained on cache. Okay, but in dynamic programming, it's not that case. We just do that. We just save it. We don't care anything about TTL. That's all. Okay, so it's a cache, compute the answer, save it in cache, okay? And whenever a request comes for the same problem, if it is available in the cache, return that answer. Otherwise, compute it, save it, and return it. Clear? This is the theoretical thing of dynamic programming. Chalo, okay? So, 4 of you clear in this point?
Yes.
Yeah.
Yes.
Okay. Deva?
Yeah. So you
Okay.
don't have a TTL in the dynamic programming, right?
Yes, we don't have anything as TTL in DP.
Yeah.
Okay. So, just one thing I want to explain I mean mention to you guys is like few guys might have already seen little bit of dynamic programming in your days, right? But it doesn't mean that you should say that okay, I'm not interested. I mean, we are going from scratch. So
Yeah.
cool. Now, so what we'll look today is we will look into 5 different patterns, 5 different patterns of DP. Okay, and most of the problems, not most, I mean, let's say some 60 to 70% of problems or few of the problems will lie in this pattern itself. Okay, and then you have some advanced concept as mentioned, bit mask DP, uh, and digit DP as such. Okay, but today we will do the general dynamic programming. Okay, so today we'll start our session with first pattern. Okay, pattern 1. Okay, so like instead of explaining theoretical wise, we will take a problem for each of the pattern and try to understand what happens. Cool?
Yeah.
Okay.
Yeah.
So all DP problems can be solved using recursion. Matlab, like
Yes.
if
Exactly.
you do,
All DP problems can be solved using recursion. Okay. So
it's just you add caching to it.
yes, the only thing we do is we add a cache to it.
Okay.
Yeah, that's all. Now, so we'll start with first pattern today. Okay. So let's take a problem for pattern 1. Okay. So what you are given is you are given an array. Okay. You are given an array of length n. What you have to tell is whether there exists a subsequence whose sum is x. Okay. So for example, let's say we have some elements. So can we form a subsequence of sum 10 on this?
Yes.
Yes.
2,
Yeah.
1, 7.
2,
Yes.
2, 5.
1, 7,
7. Can we
7,
form a subsequence of 15?
Yeah.
yeah,
Nice.
7, 3, 5, 7, 3.
2,
Uh,
5, 1,
what are those?
2, 5,
5,
1,
7, 3.
7, 3, 5, or something else also, I guess, right? 7, 8, 2, 5, 1, 7, 2. Correct?
Yeah.
Yeah.
So what you have to return is if a subsequence exists, you have to return true. Otherwise, you have to return false. Cool?
Okay.
Yeah.
Okay. So now we'll see how we can apply dynamic programming in general sense. Okay. And you can kind of see how this pattern is being applied. Okay. So the first pattern tells us we have this problem, right? So what we will do, we will we will actually look out 3 different things. Okay. 3 things on dynamic programming. Okay. The first thing is designing state. I believe you guys know what is state, correct? We have learned this.
Yes.
Mm.
backtracking and recursion. What is state?
Parameters we pass.
The parameters.
Are the parameters which are required to solve the problem. Okay. The second thing is transitions. A transition is something, your problem is dependent upon subproblems, right? So from a particular state, when we move to the smaller substates, how we actually write the transition, which is nothing but how we move from one subproblem to another subproblem. Okay. Third one is compute the answer, compute answer, save it, and return. Okay. Okay. So is the 3 points clear? We have to design the state.
Yeah.
We have to design the transition. Once you got the answer, save it and then return. Okay.
Our transition is nothing but exploring all the possible answers.
Yes.
Is that same?
Yeah.
Yes, sir. So exploring the different solutions itself, but like we write something in our method, right? In our recursion. Can someone
Yes.
please turn off that phone or whatever? Okay. Yes, sir. So what I was telling is, so from a problem you go to different subproblems and you bring your answer, right?
Yes.
So that's what transition is. Okay.
Okay.
So over the time, over 2 to 3 days of dynamic programming course, we will learn how we can design a better state, how we can design a better transition, and how we can do this. Okay. And in fact, we will learn more of the different optimization techniques on DP2. Okay.
Okay.
Shallow. So the first problem is ready with us, right?
Yeah.
Let's take the same problem. 25173. Okay. Okay. So what pattern one states is, okay. So for this problem, you will have a function solve. Again, let's think like a recursion. Okay. So what are the information which we need in order to make sure that we can achieve our answer, right? Correct. So
Yes.
obviously we want to know which number we are at. True.
Yes. Yes.
Very
Index.
much. That's pretty much sure.
Yes.
I mean, we have to know that which number we are at. That means there is something as index. Correct. Now,
Yeah.
what are the possibilities for this number? So for a subsequence, what did we learn? A subsequence, whatever the number is present in a subsequence, has two possibilities, right? Either that,
Right.
yeah, either
Mm.
that number will be in a subsequence or it will not be in a subsequence, right? True.
Yeah.
Yes.
Yeah.
So 2 has two possibilities. One is either we can include this or we cannot include this, right? So now what we have to do is we have to find whether a sum exists or not. True.
Hmm.
Whether a
Yeah.
sum exists or not. So let's say we require a sum of x.
Mm.
What are the options we have? The first option is that, dude, the first option is, okay, I'll not consider in my subsequence. Cool.
Index plus 1.
So what we do is, okay, I will not pick this number. So if I don't pick this number, how much sum still I have to construct? Still x, right? Because we haven't taken this number.
X.
Yes.
Yes.
Yeah.
What will be my second transition? The second transition is again
X minus
take
is
this number.
Yeah.
So if this is the array A, okay, then A of index,
Index.
Index.
right? So what we have done is
Yeah.
we have tried to explore two possibilities, right? The first possibility is I will not take this in my call, otherwise I will take that in my call, okay. And out of them, if any one of is returning true, can I say my answer is done? I mean, someone has returned me true. What does that mean?
Yeah.
That
Yeah.
means
There's a value
there,
sequence.
there exists a subsequence with some x, okay. Now the important thing,
Yeah.
as you guys go ahead, we have to, now whatever we are saying is, we have written a method, we have defined two parameters, right? But going forward, what we will try to do is, whenever we are writing something like this, I want each and every one of you to think of what this actually denotes. Okay, we want a definition of this, correct? So can anyone at
Hmm.
least try like what this denotes?
I mean, there are two changing parameters, right?
No, no. Okay, okay. Look, let leaves. Let me take. This is the first problem, right? So let me explain what's the definition of this. Okay, we
Hmm.
are standing at index, right?
Yeah.
So
Hmm.
this definition will tell me from index to from index to n minus one. Can I achieve a sum of x?
How is it?
Cool. So what was the question? The question was, given an array, you have to find a subsequence with some x, correct? Now I am standing at index, right?
Yeah.
So I have explored some options from 0 to index minus 1, right? I have
Yeah.
explored some options. Now I am standing at index. So what are the options I have? I have the options from index to n minus 1. Okay. So the definition will be, if I am standing at index from index to n minus 1, can I achieve a sum of x or not? Is the definition
Yeah.
clear?
Yeah.
Okay.
Yes.
For today's class, I will try to explain the definition for all of the problems, whatever we are going through. From probably from the next class, you guys should try to come up with your definitions. Okay. Cool.
Yeah.
Yeah. So now we have seen this, right? Okay. Now there are 5 things which we write in a DP code. Okay. There are 5 things which we write in a DP code. The first thing, pruning. How many of you remember this word pruning?
It's like cutting the unwanted particle, like
Exactly.
particles
So if we reach,
Unnecessary.
after a part.
yes, so if we reach at a state where we know that answer will not be possible from there, we will not go deeper and we will return from there itself. Okay.
Yeah.
The second thing is base case. Okay. That is, to which sub problem, to which little problem you already know the answer for. Cool.
Hmm.
Third problem, cache check. That is, if you have saved your answer, return it from there itself. Okay, don't compute again. If you have the answer in your cache, then return it from there. Fourth, if your answer is not there in the cache, compute the answer. Compute the answer. This is your fourth point. Okay, and the fifth point would be, save it in cache and return it. Cool. And return. So these are the 5 points which we will follow in every dynamic programming code from now on. Okay. So now let's start with our coding part, okay? And then we'll understand more about how we write these kind of stuff going forward.
Yeah.
Okay. So is everyone clear till here?
Yeah.
Yes.
Yes. Yes.
Subsequence sum x.
Some X.
Okay. Let me do initial setup. Okay. What we need? An array, right?
Yeah.
Okay. So we need an array. I'll quickly read these parameters. equals to 0. Okay. So now we are done with reading the parameters, right? So the first thing is we define DP table. Okay. So before writing DP, what's the dynamic programming? It's just recursion, right? So first what we will do is we'll write recursion. Okay.
Yeah.
Private int check subset sum x. Okay. So what are the information we need? Obviously
Index
we need
comes.
index,
Next.
sum required. Okay. Now what will be my first thing is pruning base case.
Catches it.
Yeah, cache check we will do it later since we are writing recursion now. Okay. Compute answer. Okay.
It is.
Yeah. So what is pruning? Pruning is from where we are sure that we will never get our answer. Okay.
Yeah.
Yeah. So can I say if my sum required becomes less than 0? Can I say if my sum is becoming less than 0, I will never get an answer, right? Since all the
Yeah.
numbers will be positive, if we even take or not take, can I say from here onwards we will never get our actual answer, desired answer,
Yeah. Yeah.
right?
Yes.
Okay.
So we won't get also now when all numbers are positive.
Sorry.
Like we mentioned that all the numbers in the array are positive. We won't get that case also now.
This one,
Yes, yes.
it is not required. You're
Some.
saying?
Yes, yes, I'm thinking, yeah.
Okay. Let's say Sam, we have required as 3. Okay.
Okay.
And we have the array element as 5.
Okay, okay. Yeah, got it, got it.
Yeah. So in that case, if we take that, it will become -2, right?
We are subtracting and finding the required things.
Yes.
That's it. Okay.
Yes. Okay.
Yeah.
Okay. Now we have to find out the base case. Okay. So we are very much sure that if my sum is 0, can I say I got my answer?
Yes.
Yeah.
So okay, we got
Yes.
our answer, right? There is one more case that if we have if we have exhausted the entire array, can I say I still did not achieve my answer?
Yes.
Because
Yes.
we are checking sum required equals to 0. If we have already found a subsequence with sum 0, then we are good. But if it is not true, and if we are if we have exhausted the entire array, that means we still did not get my answer, right?
Yeah.
Yeah.
Yeah. So we will return 0. Now what does 0 indicates? That we did not find out. 1 indicates we did find. Okay.
Yeah.
So what option we have? We have either not to take that, right?
Yeah. Exclude this element.
So in that case, I will go to my next index, but my sum will be still intact,
And
right? Because I'm not changing anything. I'm not even taking that.
yeah.
Okay. Another option is we can try to take that, right? In that case, if we need 5 and if we have an element 3, if we are taking that, how much we require? 2,
Yeah.
right?
Of index. Yeah.
Can I say this?
Yeah.
Yeah.
Okay. So once we are done, okay, int answer equals to 0. That means we still did not find our answer. But if any of them is giving me 1, can I say I got my answer?
Yeah.
If any one of
Yes.
is giving me 1, that means I got my answer, right?
Yes.
Isn't it clear?
Yes.
And then we finally return our answer. Got it?
Can't we make ans is equals to check? I mean, some required the two functions with place.
Yeah, yeah, you can do anything.
I mean, calling itself also we can do another. Anything is fine, right?
Yeah,
Yes.
anything is fine. I'm just,
Okay.
you just have to make sure that you are handling it properly. I'm just
Okay.
in a very naive way.
Okay.
Okay, that
Okay.
we don't have an answer, but if any one of them is returning, I am making it as one. Okay,
Okay.
cool. So this is what we have now, right?
Yeah.
So shall we run and shall we check whether our recursion is working or not?
Hmm.
Yes.
Chalo, let's
We
check.
did not call the function yet.
Nice. So we have to call it, right?
Yeah.
System dot. Okay. So from where I will start,
0.
0.
and what should be my? I should also take x also, right?
Yeah.
That is whatever is required.
Hmm.
Let it, let us make it static and we are good. Okay. Chalo. Okay. What's the example which we took? 25
25173.
25173. And what is required?
10.
So are we getting one? That means we have the answer, right?
Yes.
Okay.
Hmm.
So let's run for one more. 25173. Okay. Let's say I require 25. I'm getting at 0 because there is no subsequence which sums up to 25. Clear?
Yeah.
Yeah.
Okay. Now before
Yes.
diving into DP, I mean before doing whatever we do, what will be the time complexity of this?
2 power n.
Okay. So can you prove it? It's 2 power n.
I mean, like for every call you're calling, it'll be a tree, right? Like a full binary tree.
Yeah. So one thing is what Deva was mentioning is we have a state over here, right? From each state, we are calling two more functions. Do you guys agree? One is exclude, one is include, right?
Yes.
From here,
Yes.
we are again calling exclude and include,
Include.
exclude and include, right?
Yes.
So every time you see here, there are 2 power 0 nodes. There are 2 power 1 nodes. There are 2 square nodes, 2 power 3 nodes, right? So the tree just grows on, and at the last you will have somewhere around 2 power n nodes, right? So that's the reason it's exponential. Okay. Now if n is, let's say if n is very large, do you think your code will pass?
No.
It won't, because if n is even 50, 2 power 50 is also a very large number, right?
Yeah.
Yeah. So why do you guys think DP came into existence? In general, this problem, whatever you are seeing now, okay, let's say someone has not introduced caching, someone doesn't know caching, this problem itself is NP hard, right? It's NP hard itself. That is, you have to try out all 2 power n possibilities, correct? But why it's becoming a DP problem? The reason is of because of the constraints whatever they are mentioning in the problem. Okay. Okay. If the numbers are large, if the numbers are large, it has to be an exponential solution because you cannot cache those numbers, right? The reason it's becoming a dynamic programming problem is because of only one point, is because of the constraints. In general, you have to try out all the possibilities, but the only reason you're boiling down to DP is because of you have a certain constraints on some of the information which they are providing on the question. Okay. Now, so we found out that there are 2 power n things, right? So obviously this won't pass, so we have to use dynamic programming, that is we have to use cache. Okay. Now the basic thing is, how many changing parameters are there?
2.
Two parameters, right? So we will create
Two.
dynamic programming on two index, that is 2D array. Okay. So I'll just make it global so that we need not to pass in the function. Okay. Now you guys should tell me what should be the dimension.
N.
Okay. And this one, second one.
X, not sure.
Okay. So
1 1.
yeah, the fundamental thing is, okay, this index can have how many values? Manan, how many values it can have, this index?
All like
Yeah, all how many? Matlab, we are passing from
N.
0, right? Yeah.
Mm.
We'll have at max n values, right?
Yes.
Okay. Sahas, how many values we will have for this sum required?
It can range from 0 to X.
0 to x, right?
Yes.
Inclusive x, correct?
Yes.
Yeah. So whatever you have decided, that is what can be the maximum range, you just put those numbers up. Okay.
Okay.
This is the initialization of the DP. That is whatever the maximum range your parameters can go, just define it over here. Okay. Now, the second thing is filling your DP table with some invalid information. In my case, what I am doing is I am saying that -1. So what does -1 indicates? Your cache doesn't have your value. Okay. Is it clear?
Yeah.
Yes.
So -1 indicates that you still need to store your value. Okay. Now,
Bro, DP is 2D, right?
sorry.
DP is 2D, right? You have assigned.
No. See. Okay. So, like, are you confused on this line?
Yes, yes.
Yeah. So, what's a 2D? So, how many of you know arrays.fill, how it works? See, this is a DP, right? This is a DP table, correct?
Yes.
So, in general, I should have written 2 for loops to fill all with -1, correct?
Correct.
But DP of I is this row. DP of 0 is this. DP
Okay.
of 2 is this. DP of 4 is this.
Okay.
DP of 3 is this.
So internally it will consider the row.
Yeah, it will consider internally it will consider it as a single 1D array internally.
Okay. Okay.
So
Got
that's
it.
the reason we can do this. Okay. In
Okay.
case if we are confused, what we will do is we will make all the elements as minus. Okay. Now is it fine?
Yes. Yes.
Yeah.
Okay. So now we are cool, right? So now we have passed this. Okay. So you guys remember the 5 points we discussed? Pruning, base case. Now the third thing we have to do is
Catches.
check. Okay. If my DP of index sum required is not equals to -1, what does this mean? That my cache is been already filled by the actual answer, right?
Yeah.
Okay. So in that case, don't compute it, rather directly return it from here. Is this making sense?
Yes.
Yeah.
If you have your answer in your cache, don't compute it again, return it from there itself. Don't go more deeper. Okay. Sam and Manan, clear?
Yeah.
Got it.
Yes.
Okay.
Mm.
After this, as soon as you got the, let's say your cache is there, you will return it. In case if you don't have the value in cache, what we will do? We will store it, right? We will store the answer in your cache and we will return it. Okay. Clear?
Yes, bro.
Very simple step, right? You know recursion, you added only 2 lines check. The first line check is check whether it is there in cache or not. If it is there, return it. Otherwise, before returning, save it in the cache, return it. That's all. Okay. Now we'll run this program again and let's see whether we are getting the same answer or not. Okay. So let's take same 25173. So are we getting 1?
Yes.
Yeah.
Okay.
Yes.
One more thing, probably we can check for the empty test case. And we are getting 0. Okay.
Yeah.
So now the fact is we got the same answer, right?
Yeah.
Where is the improvement? The improvement is on the time complexity of the program. Okay. So this is a formula which you guys have to remember throughout the course. That for a DP, if they ask you the time complexity, the formula is number of states into number of transition. Okay. This is the formula which you have to remember for all the time. Okay. So what is
Yeah.
my state in this question?
Index
Two.
and X required.
Index
Like
and
required.
sum required, right?
Some
Yeah.
required.
Yeah. So my index can go up to n. Can I say that?
Yeah.
My sum can go up to x, right? This is
Yes.
n into x, right? Into number of transitions. How many transitions we have?
2.
Only 2, right?
Yeah.
Only 2. So 2 into something is constant, right? This is big O of. Okay. So big O
Yeah.
of constant into something is something, right? So big O of nx. So this is your time complexity of the code, right? So is it clear?
Yeah.
How did we derive this TC?
Yes.
So once again, can
Oh, okay, fine. So Sam, the formula is number of states into number of transitions. Okay.
yeah.
How many states we have? 2 states, right?
Okay, yeah. Two
Index,
parameters.
sum required, right? Correct.
Yeah. Yeah.
Index,
Yeah.
that is index can go from 0 to n, right?
Yes.
Sum can go from 0 to x, correct?
Yeah.
So this is my number of states. What's the formula? Number of states into number of transitions. How many transitions we wrote? Include and exclude, right, in the program?
Yeah.
Okay, transition, that means like how many
Yeah.
call.
How many recursion calls internally?
Okay, okay. Yeah.
Can I say 2?
Yeah, okay.
So constant into this is big O of, okay?
Okay, okay.
Big O of nx. So this is the time complexity
Next.
of the program which we have seen. Clear?
Okay.
Yeah.
Okay. So
Yes.
if you have observed, we went from 2 power n2. In fact, this is a very good improvement, right? This is
Yeah.
exponential and this is just some multiplication n into x. That's it, right?
Yeah.
Cool.
Yeah.
Yeah.
Chalo.
Yes, bro.
Clear now?
Yes.
Yeah.
Okay.
Yes.
So what we have learned in pattern 1 is we will define a function with some index, okay, with some required information. In this case, the only information which required was x, okay. In some other problems, they might ask you sum, they might ask you to keep what is the previous value, something like that, okay. In that case, whenever you go, check for the pattern 1 and apply and just get the answer, okay. So index comma information which is required, this is the pattern 1. Done.
Okay. Yeah, got it.
Okay, so is are 4 of you clear with the pattern 1 first?
Yeah. Yeah.
Okay, so what we
Yeah.
have learned,
Yes.
can someone just explain me? Deva, go ahead.
Yeah. Could you repeat the question, bro?
Yeah, just can you briefly explain what we have learned in problem pattern 1?
I mean, yeah. First, we'll be like taking the states that we are going to consider
Mm-hmm.
for the thing.
Okay.
Then after, we'll be like following all the like. Should I go step by step like how we explain?
No, no, don't tell the problem. Just tell whatever is required for the pattern.
Okay, fine. Yeah, first we need to go for the normal states.
Okay.
Then after we need to do the pruning.
Mm-hmm.
Then after we need to like solve the base case.
Okay.
Then after we'll be like taking if the or like we'll be like computing the answer, like if we have already solved that same set of problems, like sub problems, if it's already like present in the DP, then we'll be like considering that. Then after we'll be like computing the values. Then after if we just have like met any of the condition that we have, then we'll be like returning that answer. That's it.
Okay. So is everyone clear whatever he said, or Sas,
Yes.
Sam, Manan?
Yeah, yeah.
Sure, right?
Yep.
Chalo.
Yes.
So
Bro, one doubt is
yes.
actually whenever answer is 1, we can return directly, right? Why again checking, saving in the DP or last line 41?
Line 41. Why
Yeah.
we are saving it?
Yes, like it will be helpful only when answer is 1, right?
No, 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 not like that, Sam. See, what we just now discussed in dynamic programming is, see, these are the recursion, these are the parameters, right?
Yes, yes.
Say we have something as index 2 comma index 5. Okay. So let's say we went from index 3 to index 2. I mean index 3 with value 2. Okay. You have computed the answer. Say some other call also coming to 3 comma 2. Okay. What it will do, your recursion, it will again call this, right? Hello.
Yeah.
Repeat that 2 to 5 wala na? Like why you that second call?
We have 2 comma 5. Let's say some parameter, okay, with some information. We are going, let's say 3 comma 2. Okay. Okay. Now there are some transitions happening, and again let's say we came back to the same state. What if we don't save the answer? Again it will call something internally. If we don't save 3 comma 2 answer, what will happen in recursion? It will go again and it will compute, right? If you don't write, if you don't save the answer. Clear nahi hai?
Yeah. Hmm.
What,
Yeah.
Sam?
Yeah.
Loop basically loop is getting formed.
Yeah, exactly. See, there is a state x comma y. Okay, you are solving for, let's say, w comma z, and again this will call something internally, right? Let's say again if you're coming back again two times, 3 times, 4 times, what if you don't save the answer? You will go here every time, right? If you'll go here every time, what you're doing, you're trying to compute it, how many times it has been called, you're going again and again. Instead of going again and again, just save it. Okay, so that as soon as you come to this state, don't compute, directly return from here. ठीक है? अरे हाँ ना बोलो भाई तुम लोग.
हाँ समझ आया.
I got it, bro.
But Manan, समझ नहीं आया? अरे
He just texted me.
Sam, अरे भैया तुम लोग ऐसा करोगे तो what should I do, man?
अरे नहीं वो कंफ्यूज हो रहा है वो इसके लिए. He's getting confused.
Still you guys, you are confused? अरे still you are confused, Manan?
Manan.
मैं नहीं like Sam maybe he's offline शायद net issues he has.
ठीक है. I'm going to pattern 2. Okay, we have already
Yeah.
covered this.
Yeah.
I cannot wait much.
रिकॉर्डिंग स्टॉप करके फिर से स्टार्ट कर ले.